We've now done some basic work with the fundamental theorem of calculus and identifying simple antiderivatives, and it's worth making some notes at this point about perspectives and where does this leave us. So from some word scenario, some word problem, we end up with an integral that captures what we want to evaluate. Well, it sounds like all we need to do is find an antiderivative of what's inside, that integrand there, and then we sub in the upper and lower limits. In some cases, that's really easy. In fact, we've seen some examples already where that was straightforward. However, there are other times where this can be surprisingly difficult, and we're actually going to need to study techniques to evaluate integrals when it's not so obvious what an antiderivative is. Since that turns out to be the hard part, the idea of finding the antiderivative, we're going to introduce this new notation where instead of having an upper and lower limit, we're going to have no limits at all, and we're going to call that the indefinite integral. And the idea there is just to capture our antiderivative with the plus c here. So this is where we're always going to have the plus c. The indefinite integral, no upper and lower limits, just means find an antiderivative, or find the collection of antiderivatives without plugging in the upper and lower limits. As a point of structure or input-output format, the integral from a to b of some function is always going to be a number. It's an area, it's a value. The integral of f of x without limits is going to be a function with a plus c at the end. Number, function. That distinction will become more clear as we use it. Because of that, again, that infinitely many, we're always going to have that plus c. So if we see an integral with no limits, we will always include the plus c because we're going to get a single function if we have an antiderivative. But the indefinite integral is actually a family of functions. Think back to when we looked at those with derivatives, where we have a set of functions that are all related to each other. They're all just vertical shifts of each other. The x cubed over 3 plus c here being the general antiderivative, or the indefinite integral of x squared. Just reinforcing the notation here as a final note that if we do have the integral from 0 to 4, what we'd usually do is find the antiderivative first, and then put in the upper and lower limits as a bar here, and then sub it in as f of b minus f of a. And again, reminder, no plus c needed for definite integrals. For definite integrals, because it will always cancel. We'll always have plus c minus c if we are subbing in two values and subtracting. If we didn't have the limits, we would need to have the plus c in there. Last but not least, going back to definite integrals in particular, it turns out, because this evaluates to a number, it doesn't matter what we call the thing inside, x and x, or u and u, or theta and theta, as long as we change everything at the same time, the number isn't going to change. And the reason is, if you talk about the areas involved or implied here, it really doesn't matter what we label the axis. Do we label it x? Do we label it u? Do we label it theta? The area we get as a result is going to be the same as long as we change all the variables at the same time to a new name. So it's worth noting, and this will come up a few times along the way, that what we call the variable inside is largely a measure of convenience when we're talking about definite integrals. When we're talking about indefinite, then if x is my variable here, I should have an x when I get done. But when we talk about definite integrals, the final answer will not change if we do a one-for-one swap of a variable for another variable. So those are all properties and ideas that we're going to bring into play when we start looking at more complex antiderivatives and more complex definite integral calculations. For now, it should give you just some theory to think about.